so launching into calculus, the first topic on hand is the differential operator. So I'm just going to write it out up here for you to see. The differential operator says that if you apply it to f, it's asking you to take the limit as h goes to 0 of this function at x plus h minus the function at x divided by h. Now this may be familiar to you. This thing is the instantaneous rate of change, and you should have done that in advanced functions. So let me jot that down. Instantaneous rate of change. All right, and what you use the instantaneous rate of change to do in advanced functions already is to determine the slope of a line that is tangent to this function f of x. And you did that at a particular point. And just to jog your memory, in a moment, we're going to do that calculation with this particular function. The third thing that we're going to be able to call this is the first principles derivative. Of f. Now, that's a new word. You haven't come across derivative yet. But that there, that's the first half of calculus, is learning to take complicated functions and find the derivative of them, and then use that derivative to solve all sorts of applications. So this course is actually only about derivatives, which is a nice departure from math classes you've had so far, where it's a bunch of different ideas all wrapped together. This course is just about derivatives. The second half of calculus is integration, and integration is just this action backwards. So the entire art of calculus is taking the derivative or untaking the derivative, and that's it. He says dismissively. Now that is a lot of work, and it can be a little complicated sometimes, but you should always keep in mind that that's the plan. And the other, the message here in blue here is that this thing, this first principles derivative of f, right, when we're doing derivatives, what we're actually doing is taking the instantaneous rate of change of the function at any place, which can also be interpreted as taking the slope of a tangent to a curve, and thereby approximating the slope of this particular function at any particular place. So if we look at the parabola, and I don't want to get too much into instantaneous rate of change, because there is another video that you can watch for that, and I'll put the link on the page here somewhere, is that this parabola, the slope is different everywhere you go, right? The slope is 0 at the vertex, and the slopes are negative on this side, and they're getting more negative as you go up because it's getting steeper. And they're all positive on this side and increasing as you go up. So the purpose of calculus is to be able to find the slope of that parabola everywhere. So I'm going to use my my instantaneous rate of change on a particular point here, just to refresh your brain about how to do that. Okay, so to answer this question, find the instantaneous rate of change on f of x is 1/4 x squared when x equals 6. What you've done in advanced functions is you looked at f of x plus h, and you said that thing would be 1/4 of x squared I know the x is 6, and I've got this silly h in there. So I have to write 1/4 of the x I'm using plus this silly h squared. And then this thing, f at x, would be the function when x is 6. So f at x is going to be replaced with 1/4 of 6 squared. Okay, so I'm going to use this structure here, and I know what f of x plus h is, and I know what f of x at 6 is. So in we go. df by dx is the limit as h goes to 0 of this thing, 1/4 6 plus h squared minus this thing, 6 squared over h. All right. So 6 squared is 36, and 1/4 of 36 is 9. So I'm just going to reduce that. So 6 squared is 36. 36 divided by 4 is 9. Okay. Now, I've got this h down here, and if I put a 0 in for h, I'm going to be dividing by 0, and that's bad. So I'm hoping that I'm going to be able to manipulate this by expanding this bracket so that I can have the h's eliminate. So if I were to try that, then df by dx is the limit as h goes to 0, 1/4. I'm going to expand this thing. 6 plus h times 6 plus h minus 9. Equals limit h goes to 0, 1/4. 6 times 6 is 36. 6 times h is 6 h's. H times 6 is 6 h's. H times h is an h squared. Minus 9. df by dx is the limit as h goes to 0. Let's see, of 1/4 36 plus 8, 6 h's and 6 h's is 12 h's, and then they've got an h squared here, minus 9 all over h. So I can throw this quarter into the bracket now. One quarter of 36 is 9. 1/4 of 12 is 3. And 1/4 of h squared is 1/4 h squared. Well, here's something interesting. I have a 9 and a 9. Get rid of them. So you see how this has an h in it, and so does this? Well, I'm going to just factor those out in my next line. If I take an h out of that term, I'm left with 3. If I take an h out of this, I'm left with 1/4 h. And this is interesting too, is that h there, it's this thing multiplied by h divided by h. And if you multiply by something and then divide by it right away, it just goes away. So I can eliminate those. So df by dx is the limit of h going to 0 of 3 plus 1/4 h. Now, I can do this now. I can take the 0 and dump it into the equation because it's not going to screw it up with a division by 0. 1/4 times nothing is nothing, and nothing plus 3 is 3. That's a perfectly normal, perfectly happy answer. So I can just do that. 3 plus 1/4 of nothing is 3. So what I've just figured out there is that the slope of this particular parabola when x equals 6 is 3. So if I were to go to this location and I were to try and draw a line that does that from here, up 1, 2, 3, and over 1, up 1, 2, 3, and over 1, and then trace the pattern backwards, I'd end up with a line that just clips the parabola and takes off as a tangent, as expected, which is exciting. So this is what you were doing in advanced functions, and so you have a method for finding the slope of a parabola at a particular point. But you notice that I've got 2 more points on there in blue, and if I wanted to know the slope of the parabola at those places, I would have to repeat this entire calculation again using a 4 here if I wanted to do this one, or a -6 here if I wanted to do that one. And if I wanted to do all the points or any of the points in between, I'd have to repeat this monster calculation, and I just don't want to do that. So there must be a way for me to do this a little faster so that I can leave this place undetermined, right? Just leave it in general. So I'm going to try and repeat this calculation at on this function, but I'm not going to specify which x. I'm just going to leave x as x in this particular thing. I'm going to work through it and see what I get out at the end if I don't specify which number x is. Okay, so classic advanced functions problem. You've been handed the function, and you've been handed a very specific place where we're going to try and find the slope. So I'm using this, right, my instantaneous rate of change and or first principles derivative, in order to find the slope of a tangent to this parabola right here. So the way that we did this in advanced functions is your thing, df by dx, is the limit as h goes to 0 of this particular function with x plus h shoved into it. So that would be 1/4 x plus h squared, right? Instead of x, I wrote x plus h. Subtract the function, which is just x squared, divided by h. Okay, so to make my life a little bit easier, I see that I have a 1/4 in this and a 1/4 in that, so I'm going to factor it out. So I would have 1/4. X plus h squared means x plus h times itself, so I'm going to write it that way. Next line, df by dx. Now I have a 4 in the denominator and an h in the denominator, so I'm just going to make them one fraction, and that would make this nonsense the numerator. So that and that are in the denominator. I'm actually going to do the expansion on this, so x times x is x squared. X and an h is an hx, h and x is an ultra hx, h times h is h squared minus x squared. And if I look in that line, something really neat has happened. This is crossed out. So I'm left with df by dx equals limit as h goes to 0 of hx, oh there's 2 of them, plus an h squared over 4h. And you notice I have an h in this and an h in that. I'm going to factor it out. h, that leaves a 2x in this term, and an extra h factor in that term. And what that allows me to do is to divide out an h here and an h here, leaving me with df by dx is the limit as h goes to 0 of 2x plus h over 4. Now, something you would have come across in the instantaneous rate of change is that this limit here, up at this line, I couldn't put the 0 in for h because I'd be dividing by 0, and that's forbidden. It creates an indeterminate form. But down at this line, because I did all this expanding and factoring and manipulation of the expression, I ended up eliminating that h in the denominator. So I could put a 0 here, and I'm not creating any problems anymore because the h has been isolated up to the top and as an addition even. So I'm going to trigger this limit now that I've eliminated the h in the denominator. So I will have df for dx equals, well, the 2x is still here, plus 0 over 4. So df by dx is 2x over 4, which is the same as 1/2 of x. Okay. So you see how much handier it is if you don't put the number in, right? If I don't put in that x equals 6, then I can just follow through this and I get an equation as my answer, right? There's an equation. So why is that more helpful? Well, just a minute ago, I had to do this whole process using a 6 for x. So that would get me the slope here. But what if you wanted it at 4? Well, you would have had to do this whole process again using 4 as your x value instead of 6. And what if I wanted it at -6? Well, I would have had to put it in, put -6 in as my number and done it again. This is exhausting. I mean, it's a lot of lines for seemingly no purpose. Because if I just leave this x in general, right? I want to find the instantaneous rate of this function somewhere. If I do that, I find out that the h goes away, and I'm left with this equation. So the slope of this parabola, df by dx, is 1/2 of the x value. So allegedly, I have a little formula now that will tell me the slope of this parabola. So if I try to use that, pick one of these dots, right here where x is 4, well, apparently the slope is 1/2 of the x value. So the x value is 4 at this location. 1/2 of 4 would be 2. So if from here I draw a line with slope of 2, up 2 over 1, up 2 over 1, and then down 2 over 1, down 2 over 1. Look at that. I get a beautiful tangent line. And I did it without this process. Well, I did it by doing this process once instead of once for every dot I want to check. Let's try it on the other side using -6 for my x. So 1/2 of -6 would be -3. So from this dot, I'm going to drop 3 over 1, drop 3 over 1, drop 3 over 1, and go the other way. Look at that. Another beautiful tangent line. This comes in and clips the function. I didn't have to do this at x equals -6. I just left it in general. So what we're going to do in calculus here is we're going to take this idea, the first principles derivative, which is essentially the instantaneous rate of change, and we're going to apply it to all of the base functions. And we're going to get little rules for this so that we never have to do this process again. And as we make rules for more and more complicated functions, then we're going to be able to sketch more and more complicated functions, because we'll be able to not only get intercepts, which you could already do in advanced functions, but now we can find slopes of functions so that when you're sketching it, you can make sure that the slope is right, the curvature is correct. So I'm going to erase this, and then we're going to try and do this on a line, just so that we can go through and we can check what the A's, the P's, and the Q values do when they're exposed to this particular operator. Okay, so to investigate what happens to an A value, I'm going to use just a basic unadjusted parabola, and I'm going to tack an A value in front. So I'm going to be working on this function, g of x is a stretched parabola. So this thing will either stretch it or compress it or flip it, whatever number I choose to put in there. But I'm going to leave it generic so we can see what happens to this letter regardless of what it is. In order to fill into this, I'm going to need my x plus h term. So I'm going to write this again, g of x plus h. And I'm just replacing this with an x plus h. Alright. So in the last example I had a quarter x squared. This one I'm just leaving this undefined to see what happens to it as I go through. So I'm going to take this, it goes here, this, it goes here, in order to work with my differential operator. So the differential operator applied to g would be the limit as h goes to 0 of this thing minus this thing okay. So I have an a there. I'm going to factor it out of each term. Just left with x plus h squared minus, nope, factored that one out. Okay. I'm going to have to expand this bracket, and in the problem sets you're going to get to this point and you're going to have to do it too, where if you have an x plus h cubed, you'll have to do the thing times itself, or if it's power 4, you'll have to do the thing times itself, in order to work through this particular algebra. For here, I saved the simple one for me. dx would be limit h goes to 0. This a is hanging around. The top here would be x plus h multiplied by itself. This should be looking awfully familiar to what I had down here when we did the derivative, or the instant rate of change on 1/4 x squared. This little structure should be very similar. That's not an accident. I mean, all parabolas have a very similar structure when you get through this calculation. Limit as h is 0, a, x times x is x squared, an x and an h is xh, an h and an x is another hx, for a total of 2xh. H times h is an h squared minus x squared all over h. Now, just like in the 1/4 x squared example, this x squared and this x squared ended up undoing each other. And I'm left with two terms in the center, each of which contains an h. So I can factor that one out. Limit of h goes to 0 of a. This thing has an h. If I take it out, I'm left with 2x. If I take one out of here, I'm left with h. And it's happened again, just like in the 1/4 x squared example. I have this 2x plus h multiplied by h divided by h. So these two have undone each other. And I'm down to dg by dx equals the limit of h going to 0 of a times 2x plus h. And finally, at this line, I've reached a place where it's safe to actually trigger the h equals 0. Because it's not going to be dividing by 0. It won't create an indeterminate form. So I'm going to do that. I'm going to pull the trigger and let h go to 0. So I end up with dg by dx equals an a 2x, and plus 0, which is just gone. Now, if you look at that, notice that this was every parabola that hasn't been shifted. So if your parabola's vertex sits on the origin, it doesn't matter what a value you use. You could make it twice as tall, thrice as tall, half as tall, reflect it underneath the axis so it's upside down, stretch it any way you like. All those parabolas are contained in this little expression, this generic parabola. And if you have the generic parabola like this, then that's its slope. You don't have to do this again, right? This is non-specific, right? I didn't assign this a value. I didn't pick a particular place, but I was still able to figure out what the slope would be if I told you the stretch and if I told you the place. And that's where we're going in this course, and that's what's really powerful about calculus, is it's allowing you to leave the realm of questions that happen here and expand into, well, if I have information about here, what's it doing everywhere else? So that's, I'm not sure if you can appreciate that at this point, but that's very freeing, right? Like, this is the keys to the kingdom. Suddenly you can do problems that seemed or would have been impossible even before this. Like, well, what were we, 30 minutes into the video? Okay, good. So I've just figured out that if your function is a stretched parabola, then the slope of it, dg, is that stretch times 2x. X squared becomes 2x. Wonder if there's a pattern there. Okay, on we go. I'm going to try taking this parabola then, and instead of stretching it, I'm going to move it around. I'm going to put a p value and a q value in there, and I'm going to see what we get. All right, so using the parabola again, the type of function I'm working at will be, let's say, k. K of x is a parabola that has been shifted to the right a little bit and raised up or down. So that's what that would look like, right? There's your rightward shift, there's your up or downward shift. So that's what I'm going to put here. What I need here is the same thing, k of x plus h, but I'm going to replace the x with an x plus h. The minus p is still there, and the plus q is still there. So in it goes into my instantaneous rate of change equation. So the differential operator acting on k would be the limit as h goes to 0 of this thing plus h minus p squared plus q. I'm just going to pop that in a bracket so you can see that that came from the first part, minus this all over h. Okay. So, carrying on. This is going to look like a heinous amount of algebra, and someday you're going to look back on this video that you thought had a heinous amount of algebra in it, and it's going to be so cute and small, and then you will weep for the mess you have made. Anyway, so this thing here, I've got nothing multiplying this bracket, so I don't really need it. I've got this bracket multiplied by itself, so I'm going to write that out. X plus h minus p times x plus h minus p plus q. This has a negative in front, so that negative is going to affect that pod and that pod. So we're going to have minus x minus p multiplied by itself and minus q, like that, all over h. All right, now I've got my fingers crossed that things are going to start going away because this is becoming a mess. So if I scan across, I have plus q minus q. Gone. And if you take a gander across, you notice there are no q's left. So it looks like this thing here doesn't matter. We'll come back to that and talk about it in a minute. All right, so continuing on, I'm going to just switch colors so you can see what's happening here. I'm going to have to do massive expansion on this. Everything in this multiplied by everything in this. X and an x is an x squared. X and an h is an hx. X and a p is a minus px. H and an x is an hx. H and an h is an h squared. H and a p is a minus ph. Minus p and an x is a minus px. Minus p and an h is a minus ph. A minus p and a minus p is a plus p squared. Whew. Then I have subtract, and I have to do this expansion. X and an x is an x squared. X and a minus p is a minus px. Minus p and an x is a minus px. And minus p and a minus p is a plus p squared. Goodness. And all of that is divided by h. Now that is a lot of stuff. But this line is the place where things started to cancel in all of the other examples. So I bet a bunch of these terms back here are going to eliminate a bunch of the terms up here. So let's go through and see what we can find. I have an x squared, subtract an x squared. Gone. I have a negative px minus a negative px. Gone. I have an ultra negative px minus a negative px. That is gone. And I have a p squared subtract a p squared. Gone. All right. So let's dig through here and see who survived. dk over dx equals limit h goes to 0. I have an hx. Actually, I have two of them. 1, 2. It's gone. I have an h squared. I have a negative ph and a negative ph. That's two of them. And that's it. Everything else is gone. All right. So, just like all of the other examples, most of the mess took care of itself there. I only have a few terms surviving, and note, every single one of those surviving terms contains an h. If they don't, you've made an error in this line. You need to have the h there so that you can factor it out in order to divide away this one. So I'm just going to do that, factor out my h's. that leaves a 2x in this term. It leaves an h in this term, and it leaves a minus 2p in this term. Alright, as predicted and as expected, this h divides away that h. I'm left with dk by dx equals limit h goes to 0 of 2x plus h minus 2p. I can put the 0 in for h reasonably harmlessly, so if I do that, that's gone, and all I'm left with is 2x plus, nope, 2x minus 2p. And if I factor that 2 out, I end up with this. So let's look at what happened in this little process. As I mentioned before, the q vanished. Now q is a shift up and down. And this thing is asking about the slope relative to where you are on the x-axis. So if you had a slope here at a certain value, and you just take that function and slide it up or down, you are not changing the slope over top of that point. So this shouldn't matter, and the algebra took care of it, vanished it for you. If you have a slope over this particular point and you shift the thing that way, then this slope should show up over there. So the slope expression needs to be shifted as well. And look what happened. That shift to the right showed up in our slope expression. It's nifty when that happens. So it looks like when you do this differential operator, A values survive, P values survive, but vertical shifts disappear in the mess. So the last thing I'm going to do here is a parabola in standard form so that we can see what happens when you have a function plus a function. So this is starting to look like a parabola in standard form. So what happens when we apply the differential operator to a parabola in standard form? Well, I'm going to need m at x plus h here. So m at x plus h would be x plus h squared plus x plus h. So I'm going to drop that into my differential operator up there, and I'm going to see what happens. So the differential operator acting on m would be the limit as h goes to 0 of x plus h squared plus x plus h minus x squared plus x. All over h. Now I'm gonna shortcut here a little bit. Work smart, not hard. In the next line, I'm going to distribute this negative. Let's just do that one step at a time. So that will make this minus x squared and minus x. Okay, now I'm gonna switch the order of these two things. I'm gonna write this before that. You'll see why in a minute. So I have x plus h squared, and then this thing is subtract x squared, so it comes first. This is add x plus h minus x over h. Now, the neat feature of fractions is that I can take this whole mess over a single denominator, and I can break it into two fractions with the same denominator, like that. Maybe you see where this is going. And if I'm going to take the limit of this thing, it'll have a value, like, I don't know, 8. And the limit of this thing will have a value, whatever it is, maybe 3, and then you just add them together. So if I can do the limits separately, I'm just going to write them that way. Okay, now I'd like you to take a look at what I've got there. This thing, the differential operator acting on M, which was a standard parabola plus a standard line, equals the limit of a parabola with x plus h shoved in it minus a parabola over h. Well, that's this for a parabola. So this thing here is just the derivative operator acting on an x squared. And this thing, the limit of f of x plus h minus f of x over h, well, this is just the derivative operator acting on a line. Now, do you see what happened? I applied the derivative operator to M, and I could shortcut by just applying it to each of these components separately, right? If they're, as long as they're separated by a positive, like a plus or a minus, there's a word for that. It's distributive. So I'm going to erase this, and I'm going to show you what that looks like with the operator in a second. But I want to really underscore that we already know the answer to this, and we didn't actually have to do any of this limit stuff, because I already know from previous examples that the slope expression for a generic parabola is 2x. And I already know that the generic answer to this, right, it's just the slope of this line, and this line has a slope of 1. So there you go. Now the algebra in this, right, like this is a lot of work, but if you can appreciate that at the end, this little bit of justification is allowing us to build patterns so that I can say, well, this function is two things added together. So if I could apply the differential operator to this one, get the answer, and this one, get the answer, I would have my full answer because I can just do it in separate parts. And if I can, even better, break those separate parts into things that I already know the slope expression for, and I can skip all this garbage in the center and go straight to my slope expression. That's very powerful. And in the next section, we're going to talk about patterning a little more so that you can go straight from this type of function to that type of function. So I'm just going to erase this, and I want to write out this distribution stuff a little more explicitly so you can see what I'm doing. Okay, this is what I started with. My function is a standard parabola plus a standard line. And you were asked to apply the differential operator to that function. So I did. Now, one of the foundational ideas that you should have picked up from algebra is that if you do something on the left side, you must do it on the right side as well. So there you go. Now the next line down, I cleaned this notation up because this is a bit awkward. I just said, well, we're going to let the derivative operator act on M. But what happened next was that I said and then calculated and figured out that I could do the derivative on this separately. So like having a negative here, a negative goes on to each piece that's separated by a plus. I'm going to do the same thing. I'm distributing that operator into the bracket. So because I've distributed it, because it has that, let me write that down. The differential operator is distributive. Because it has this property, I can just allow it to pounce on everything inside that bracket. And so now that I've got that done, I can see that the derivative operator acting on m is just the derivative operator acting on x squared. And I already know the answer to that. It's 2x plus the derivative operator acting on x, which I already know is 1. So all of the algebra that came before, all that limit stuff, all this, is really just justification, like the foundation, the cinder blocks that sit underneath calculus. And we're going to eventually transition into something more like this, because this is better, right? It's faster, it's more efficient, and it's going to let us solve more complicated problems if we can do it by patterning. So the problem set is going to ask you to do this operator on an x cubed. It's going to ask you to do this operator on an x4. And then it's going to ask you to do it on a summation of 2 bits. And then it's going to ask you to think about patterns. Right? If the differential operator turns an x squared into a 2x and an x to the 1 into 1, I wonder what the pattern is for the other polynomials. So think about that, and then in the next video we're actually going to work that out and see what the pattern is.